So now we have the question of how do we want to implement sequential logic, things like latches and flip-flops on the cell matrix. And again, we have a choice of two strategies. We can take the standard digital logic approach and build, for example, a pair of cross-coupled inverting gates like this. Feed the inputs in there, read our Q and Q bar off of the outputs. And that's fine, but it's actually a bit of overkill because the individual cells of a cell matrix can do more than simply act as a two-input gate. So here's a strategy we can use to implement, for example, a D latch. So we're going to have two cells. The cell on the right is simply going to circulate whatever value is coming in from the west. And on the east here, we're going to have a piece of data coming in on the bottom, and we're going to have a load line coming in on the north. And we're going to put the following equations in here. The equations in this cell are going to be simply data east, so that's the data coming out here, is equal to our load line ANDed with the data line coming from the south, or if load is low, we're going to take the data coming from the east and send that back out. So whatever data we have coming in here, if load is low, simply gets circulated back through here, and we have a bit trapped between these two cells. But if we raise the load line, then the data coming in from the south, this D line, gets sent through to the east and comes back in, and then when the load line drops, the last value that we had coming from the south will start being trapped in here and will circulate, and so we'll be able to load a value into this two-cell D latch by putting a value on D, raising the load line, and then dropping it. So the actual Boolean equations in here would be something like data east equals north-south or north bar east. That goes inside here. And while this is taking two cells to implement a single bit, this cell is only being used to recirculate. Oh, and we need an output here also, so let's just send the output value to the north for no particular reason. So the equation in here is basically data west equals west and data north equals west. Well, if we wanted to implement a 2-bit latch, we don't need another two cells because in fact this cell is only using the northern output and the western side, and this left cell of a 2-bit latch does not need the northern output or anything on the west. So we could also put a load line into here, put a D bit into the south, put another recirculate cell over here, send this out to Q, and now we can call this D0, D1, Q0, Q1, load 0, load 1. And we can put the same equations in here. Instead of just data west equals west and data north equals west, we can also add data east equals north-south or north bar east. And then in this cell, we can have the equations data west equals west, data north equals west. And so now we have 3 cells implementing 2 bits worth of D latches, and this asymptotically comes out to be 1 cell per bit. So if we have 100 bits, we can implement it with 101 cells. So this is an example where we can take these cells and we can use them for multiple purposes. This cell is both the refresh part of this latch and also the input control part of this latch. So we can usually do better than just starting with a straight digital circuit using simple logic gates and implementing that directly on cells. You usually get a better implementation if you think of these cells as being more powerful blocks and you work from that point of view.